So welcome to Science Unwrapped. Thanks for coming out. This is the last of this year's talks from our 10th anniversary celebration series, which has looked at powers of 10 from cosmologic scale, the largest of scales that we know anything about the science of. And tonight we go to the teensy tiniest, the quantum scale, and our speaker tonight will tell us what that is. Is there anyone here who hasn't been to a Science Unwrapped before? Yeah, okay, I'll tell you how it works. So we'll be in this room for about an hour until 8 o'clock, and our speaker will talk for 40 to 45 minutes, and then when he's done, we'll have time for questions and answers. So at the end of the presentation, don't bolt from the room unless you really have to. If you stay in your seat and be reasonably quiet, then we'll all be able to hear the questions and answers. And then at 8 o'clock, we stop in here, we'll say thanks to the speaker, and there are lots of activities and demonstrations and people to talk to out in the hallways on the first floor and in the basement. So if you want to play around with science from other groups here at Utah State, stick around for the fun. So our speaker tonight is Dr. Charles Torrey, or Charlie, I will call him, who is a physicist. Charlie grew up various places around the Midwestern United States, and then he did his college and graduate education in North Carolina, where he did a PhD or a BA in physics, BS in physics at Duke University, and a PhD at University of North Carolina. So he's probably another basketball fan like we had last week. He then was a postdoc in a number of places, including London, New York, Florida, and University of Utah. And 28 years ago, he came here, where he's now a professor of physics and also an associate department chair. He studies mathematical physics, gravitation, quantum theory, and a lot of things that most of us have heard about, but probably don't really know what they are. I sure don't really know what they are. So he will tell us tonight about what you find and how it works at the tiniest of scales that exist. Is that right? Not just that we know how to study, but that exist. So I'll let Charlie take it.
Thank you. Can you hear me okay? Yes? Yes? Okay. All right. Cool. Right. So I thought, since this is the last, that's interesting. Let's do this. This is the last session of the Science Unwrapped, the 10th anniversary year. It would be worth at least mentioning the people that is this working? No, not yet. Let me make this go. I'd like to mention some of the people that have made this thing go over the years while I fix this. I'll let you stare at those names while I fix this little device here if I can. Doesn't matter. So can you see some names there that you recognize perhaps? The beginnings of this thing were Shane Larson and Michelle Larson, Mary Hubbard and Marianne Muffaletto, who's still going strong helping us with this stuff. And I also would like to maybe mention Nancy, who just spoke to you. She is our fearless leader these days and has made this thing keep going as strong as it is. Okay, so now I'm going to just install this little guy here. See if that doesn't help. Maybe, maybe not. Yes. So I also want to thank you, because without a community of fellow science geeks to share our enthusiasm, there's really not much to do here. This whole thing would be kind of boring. So thank you for being here, and thank you for supporting us all these years. Okay, so the theme, because this is the 10th anniversary, the theme of this whole series is powers of 10. And we've been using powers of 10 to sort of organize distance scales in science, starting last fall from the very largest distance scales, the scale of the universe as a whole, and studying scientific phenomenon at ever decreasing sizes. Okay. And today, of course, we're going to get to the smallest, at least the smallest scale that we're going to talk about this year. And to orient you just a little bit, let me remind you just a little bit about this. Okay, so if you think about the observable universe today, up to give or take a few feet, it's about 10 to the 46 meters in size. Okay, it's just an order of magnitude estimate. That's a 1 with 46 zeros. So it's a big number. It's like unimaginably big. as is the universe. Okay? But it helps to use these powers of 10 because at least we can use the 1 with the zeros to help us keep track of how big or how small things are. So we can go down to a more manageable size. The size of this room, I don't know how big it is exactly, but I picked about 10 meters. That's about 30 feet. It's not how big the room is, but it's sort of in the ballpark of how big this room is. So 1 with 1 0, not so hard to get. So this distance scale of everyday phenomenon, like us, is very familiar and also has a very simple number attached to it. Okay? We can go a little smaller. We can go about 5 orders of magnitude or 5 powers of 10 smaller. And now we're talking about a typical diameter of a human hair. So 5 orders of magnitude gets you from the size of this room, give or take, down to about the size or diameter of a hair. Okay, so that sort of gives you a feel for what you're doing when you're going to smaller and smaller distances organized according to powers of 10. You can go a little further, another 6 orders of magnitude, another 6 powers of 10. Now you're at the size of atoms. And at the atomic scale is where the quantum physics starts to take over. This quantum reality I want to try to describe for you today is appearing here. Okay? And in fact appears here and at all smaller distances as well. You can ask, how small can we go? And the answer is not known, of course. But what we do know how far we've gone, and it depends a little bit on how you define small now, but if you look at what is being measured at the Large Hadron Collider, which is in some sense the biggest microscope, it's not really a microscope, but the biggest machine in the world for looking at little things, this Large Hadron Collider, which is in Switzerland, has observed phenomena which you could characterize with a length scale of about 10 to the minus 18 meters. So that's 0.000018 times. Okay? It's a very tiny thing. It's about 8 orders of magnitude, 8 powers of 10 smaller than an atom. That's how far we've gone experimentally, give or take. Okay? Now you can imagine going smaller. You can go to a length we like to call the Planck length, but now we're in a very speculative world where nobody really knows what's going on. There are lots of ideas about what happens between the 10 to the minus 18 that we sort of know about and this 10 to the negative 35, which is really small, right, that we don't know about. But while we don't know what's going to happen if we start exploring down there, and you can be sure somebody will start exploring down there as soon as they can, we do know, or we do kind of think, based on what we know now, extrapolating what we know now, we kind of think that when you get to 10 to the minus 35 meters, the notion of distance itself ceases to have any meaning. And this is a quantum mechanical phenomena that causes this. I won't go into that because it's all very speculative. Today, even though I'm just a theorist and I like all these speculative things, I only want to tell you about things that we kind of know. In science, to say you know something means you can verify it repeatedly in the laboratory. So I only want to talk about things that have been well tested in the laboratory, even though there are lots of interesting ideas that might happen in the future. Okay? So this is considered the theoretical limit to how far we can go. Okay? Now what happens after that, it's not clear even how to ask the question. And without experimental data, probably it's foolish to speculate too much. But what I want to point out is that here we are at the level of atoms, 10 to the minus 10, which we know very well in science. From the room, we went from 10 to the 1 meters down to the smallest possible distance, 10 to the minus 35 meters. What do we have? 36 powers of 10 there, 36 orders of magnitude difference. So it's kind of getting up as much as you go, if you want to go from this room to the whole universe at 10 to the 46 meters, this is 45 orders of magnitude. We're used to thinking of the great frontier of exploration is to go out into the universe, and there's lots of room to do it. But I think you can see from these numbers here that, as Richard Feynman likes to say, in an old talk of his from the 50s, there's plenty of room at the bottom. Okay, and lots of interesting physics and scientific exploration can occur at the smallest distance scales. Okay. All right, so quantum physics has been around for about a century. Our knowledge of this quantum reality, which I want to describe to you, has been known since the 1920s, say, based on experimental investigations. And I want to tell you some really interesting things, and I want to actually kind of try to blow your mind a little bit if I can. I may not succeed, but I'm going to try. And, but before I do that, maybe I should just tell you that these investigations into the quantum nature of reality were not motivated by any attempt to find practical applications. These investigations were pure science investigations. People were just looking at smaller and smaller distances because they thought it was interesting. They were curious. They were explorers. But as often happens in science, pure exploration based on curiosity usually leads to some practical advantages. Okay? You never know, unfortunately, which pure science investigation will lead to these practical advantages, but you know you're going to get some eventually. And quantum mechanics is a great example of it. In fact, as my good friend and colleague David Peake says, quantum mechanics is money. This is, I stole from his, who was also one of our Science Unwrapped speakers not too long ago. David Peake has this in his lecture notes for his introductory quantum physics class. And the idea here is that a big chunk of the world's economy is based on technology that only exists because of the existence of this quantum reality. Okay? And I could spend a whole talk on this, except I'm not very good at this kind of stuff, the practical things. So I won't. But let me just mention one example. Okay? So you may remember that in the olden days, this is what a telephone looked like. Eh? Anybody remember this? Anybody ever have one of these? Yeah, my boss, yeah. So he probably still has one, actually. But back in the old days, they had really big pockets, right? So, of course, now we have the quantum telephone. And these beautiful, powerful devices we all carry are made possible by, of course, microchips built out of semiconductors. And these semiconducting materials are being used, the way they're being used is to take advantage of quantum physics. So that's just an example, and you can imagine how the world would be without modern computational technology. Okay. All right. I probably will fail miserably in trying to explain to you the coolness of quantum physics because it's a little tricky, right? It took 100 years to figure it out. It's not going to be done in 30 minutes. But there are three things I want to try and show you. There are many possible angles on quantum physics if someone is trying to understand what the heck it's all about. Okay? But I picked three. Maybe they're not the best three, but they're the three you got. So here we go. The first one is going to be size matters. Okay? Second one will be particle wave duality, and the third will be something called superposition. Okay? Try to give you a feel for what these words mean as we go. Okay? So the big question for us today is, what's it like down at the realm of atoms and smaller? This is the quantum realm. What's it like down there? In order to kind of get you thinking in the right mode, I brought some toys. I need volunteers. Okay. Use my microphone. It's okay. Okay. I see these hands out. I promise I will try not to hurt anyone, but it could happen. Okay. I need somebody to catch this thing. So for this one, you're going to need kind of big arms. I need somebody with some arms. I see you. Can you try to catch it? All right, catch it. Piece of cake. You can keep it. I don't want to take that back to my office. All right. Nice job. Let's try something smaller. Now, smaller arms are in business. Okay, buddy, here you go. Good catch. Well done. Wow, I didn't expect this kind of success. Okay, let's try something a little smaller. Really? You want this? This water balloon? No, I don't think so. I can't do it. I get in trouble. I can't do it. Here's something nice. Here's a nice one, okay? Something soft and easy, okay? Can you catch it? Try. A little harder because it's smaller. Good catch. Well done. It's hard because they're smaller, but that's not the point of this exercise. Okay, let me go one time smaller, okay? And then I'll tell you what this is all about. Who wants this one? Oh, you already had one. Who wants one? Wants one? Ready? Oh! That's ping pong balls, sorry. Okay, so what's the point? All right, the point is, to my surprise actually, these kids here are pretty good catchers. And they kind of knew where the ball was going. Every time, didn't matter the size. Every time I threw it, they did this calculation in their head without thinking, of course, and put their arms right where that ball was going to go. We know from experience how things move. Now, physicists will write down a whole bunch of mathematical equations to precisely indicate where everything will go if you throw it. Okay? But we do it with our brain instinctively. It's quite remarkable. Okay. Now, you can imagine repeating this experiment that we just did over and over again with ever smaller objects, you know, maybe a marble and a pea and a grain of sand, and just keep going. And you could finally get down and start throwing tiny little balls, which you might think of as electrons, like little particles that go in the atoms. All right. One possibility is that as you shrink everything down, it's the same as what we just did here, only smaller. Okay? That's one possibility for what happens down at the atom scale. It's just like everyday life, only smaller. That makes you think of a very familiar picture, right, of an atom. So my question for you is, I want to take a survey. Who has seen this kind of a picture in their schooling? They're still doing it. I see young people do it, old people for sure, like me. You've seen this picture. I call this the solar system model of the atom. So it's just a big solar system shrunk down. Instead of the sun, you have the nucleus. Instead of the planets, you have the electrons. And this is how people thought of atoms prior to the discovery of quantum physics. Okay? But I want to tell you that this is exactly the wrong thing to have in your mind. Do not think about this anymore, ever. Okay? This is one of my biggest pet peeves. Please don't. This is not what atoms are. If you're going to have a mental image of an atom, you must not have this. And if only for one reason. And the reason is that if you shrink down a solar system to atomic size, you can show, using the rules of everyday life, that these atoms are unstable. They actually decay by emission of light, and they collapse in a fraction of a second. So these atoms don't exist. And before quantum mechanics, people thought atoms looked like this. They kind of knew there was a problem. But they figured if they got more experimental data, they could sort out what was going on with this instability business. And instead, they threw out this model and replaced it with the quantum model, which this is the mental image I want you to have in your mind when you think of atoms. Okay? This is actually a whole bunch of different possible behaviors of one single electron in a hydrogen atom. So one electron going around a nucleus. Each one of these is a possible behavior of that electron. So just pick any one of those pictures. That's the electron going around the atom. Okay, the so-called electron cloud. Okay, that's what I want you to put in your mind, because that's much closer to what these atoms are doing than that little solar system business. Okay. Now these are textbook pictures which I ripped off from Wikipedia. Okay, so it was okay. I was allowed. And these textbook pictures, these are predictions made by the mathematics of quantum mechanics, and people knew about this for a long time, and all the theoretical work that goes into making quantum mechanics make iPhones and everything else uses these kinds of pictures, or the mathematics behind them anyway. Okay. But recently, relatively recently in the history of the subject, people actually can image these things now. We can make images of atoms. And here's one I found recently, an experiment from about 15 years ago in Europe, I think. Came from some work in Europe. And what you're seeing on the top picture there, up at the top, right up here, this is the actual data. And what they've imaged is the outermost electron orbital in a nitrogen molecule. And this is what they see when they image it. Now, how do they image it is the tricky part. That's the experimental brilliance of the authors here. What they did was they blasted this atom with a very high-frequency laser. And watched by the way the light came off, they were able to get this picture. And this is, again, this is the image of an atom you should have in your mind. It's actually a molecule, but nonetheless, this is an electron, a single electron in a molecule. Okay? That's how you should think of it anyway. And of course, I'm lying about all this a little bit, but you know, you get the idea. Okay. All right. Okay, so my point there was size matters. What's happening at the very smallest distances, atomic and smaller, is very, very different from what you see in everyday life. Okay, that's why it took so long to discover it. Now I want to move on to the second point, this thing called wave-particle duality. It's one angle on what is different about the very, very small compared to the very, very large. And so we threw some balls around and fooled around and had some fun. Even maybe I have some more I could throw, but anyway, maybe later. And those things were just little objects flying through space, and we used to think that's what particles were. But it's not at all true. But there's a reason why people thought that. You can do all kinds of experiments where you shoot electrons at things, like shoot electrons at a surface, like a table, and they bounce off like throwing a ball against the sidewalk, you know, like a tennis ball on the ground. So there's all kinds of experiments you can do. People have been doing them forever. Electrons do act like that. That's like a little ball bouncing around. Okay, so that's a particle-like feature of an electron. There are other features, though. Let me show you an experiment that has now been done. It used to be just a thought experiment that people made up in their heads, but people have actually done these measurements now. You can take this thing at the top here is an electron gun. It just fires electrons out. This thing is a barrier, and if you had no holes in it, the electrons would just bounce off like I showed you in the previous picture. Okay? But instead there are a couple of holes in it, okay? And the electrons go through and they make this beautiful pattern. What you'd think would happen is you just get two blobs, one behind this, the right-hand hole and the one behind the left-hand hole, where the electrons hit this detection screen here. But instead you see this pattern. It's called the interference pattern. And this interference pattern is easily understood if you're a person that works with waves, water waves, light waves, any kind of waves passing through holes. Here's some waves, these vertical lines. They hit these holes and they make these spherical waves. You've seen stuff like this whenever you're on the water. And it's the combination of these two waves that makes this pattern. So in this experiment, the electrons are acting very much like waves. And this sort of experiment has been done. In fact, I think these are data from such an experiment. Okay. Here's another one. This is called electron diffraction. On the left, one is shooting X-rays, which are really just light waves with very short wavelengths. It's the same phenomenon. They're waves passing through an aluminum foil, very thin aluminum foil. And because of the interaction of the light waves with all the atoms, you get this very nice circular pattern coming out on the other side of light. It's X-rays, really. Okay. You can shoot electrons at the same foil, and you get a big spot in the middle where all the particles go, but some of the particles go out here. And every time the electron hits this screen, it makes a white dot. And you shoot a bunch of electrons here, you get the same kind of pattern. And the only way to explain this diffraction pattern is to think that the electron has some waviness to it. And these are real photos from some ancient textbook. So the perennial question is an electron a particle or a wave? What's the right way to think about it? Because it exhibits both features. And as always in quantum mechanics, there's only one answer, and the answer is, of course, yes. That's the way it always is. Okay. Okay, so let me tell you a little bit that you can do with this idea, okay, just real quickly. Okay, so I start with a riddle. When is a barrier not a barrier? My wife always tells me I'm terrible at riddles. I don't even understand punchlines to jokes. I don't even know if this technically is a riddle. I don't even know what a riddle really is by definition. But this is what I got, okay? So when is a riddle, when is a barrier not a barrier? Here's my answer, okay? Windshield. So a windshield is certainly better be a barrier. It stops rain, stops wind, stops particle-like things. It's a barrier to particles. But of course a windshield is useless if it isn't allowing something to go through, that is to say light. Light must go through, and light does go through. That's why we see through it. That's the wave nature of light is allowed. The particle nature of water, say, is not allowed. All right? And so this is an example where a wave can penetrate something that a particle cannot. Now an electron has both. So you can imagine shooting electrons against a barrier. This is a crude diagram of a barrier here. And the electron has this sort of particle and wave feature. And the particle wants to bounce off, but the wave feature likes to leak through a little bit. But the wave is also a particle, so it's possible for this particle either to bounce off or just magically appear on the other side without ever going through the barrier. This is called quantum tunneling. It's a real effect, and it's a manifestation of that wave-particle duality. Okay? And there are lots of interesting applications of this effect. I'll just show you one because there's a cool picture that goes with it that I really like. Okay, this is the application I want to talk about. It's called the scanning tunneling microscope. Many Nobel Prizes awarded for this device. What they do is they apply a voltage to a bit of metal near the surface of a material, and that changes the barrier that holds the electrons in the material just enough so that a few can leak out through tunneling. And the amount of electrons that leak out depends on sort of what the surface is doing where the little bit of metal is. And they can make a map of the surface this way. And the resolution of the map, they can see things, structures at the size of atoms. So in this picture, in fact, this is an IBM photograph, or reconstruction of data, I should say. These things here are the atoms, actually. They don't look like little solar systems, do they? These are atoms. The IBM people were able to show that this tunneling thing could also be used not just to look at the surfaces, but actually to manipulate the surfaces. They picked up atoms and put them in this, what they call the atomic corral. And I thought since you were in ag school, you know, the livestock thing is good. So I picked the corral. But there's a bonus to this picture. Okay? So this picture was made using that tunneling phenomenon. These little wavy things are actually electrons. So these are the electrons at the surface of the material. They don't look like little balls flying around. So this picture speaks 1,000 words. It's a really great one. And so it's quantum mechanics at its best right here. Okay, particle wave duality, done. I had about 15 minutes. Let's go to the last thing I want to tell you about in quantum theory, quantum physics. This one is the biggest mind blower, and it's hardest to explain. And so to explain it, I'll have to use cheap analogies, okay? So as not to bore you to tears with technical stuff, okay? But we'll use cheap analogies, and like all analogies, they're good because they're simple, but they're bad because they're wrong, okay? So they'll be lying a bit to you. You have to remember all analogies are imperfect, but I'll do my best, okay? Just to give you a feel for what's going on. If you really want to know what's going on, you got to come and take physics. You got to take physics from, I saw Maria Rodriguez here. She teaches quantum physics. So does Professor Peak here. Come to the physics department. We'll show you how to do this business. Okay? So I call this superposition. Here's the idea. Okay? Again, crude analogies. Think of a traffic light. You know, when you look at a traffic light, there are three things you can see: red, yellow, or green. Now, when you pull up to a light at an intersection down on Main Street, of which there are too many, you will find that you get red, yellow, or green, and without thinking too much about it, the chance of getting red is 1 in 3. The probability for getting yellow is 1 in 3. So statistically, it's 1 in 3 for each possibility, red, yellow, green. Okay, that's fine, no big deal. But you know, as soon as you look at it, then you'll see which color it is. If you're driving, you better be looking at it, right? So that's how everyday life works. But the quantum version of this at the very small distance scale is very different. Quantum physics asserts that this traffic light is in all three states at once, red, yellow, and green, with about a third probability for each one. And quantum physics moreover asserts that that's the best you can do. If you want to find out, if you want to commit to what that light is actually doing, you must look at it. You must measure that color. So unless you look at it, it's all three at once, in a sense, in a statistical sense. It commits to which color it is when you look. This sounds very airy-fairy, I know. It's like if the tree falls in the forest, blah, blah, blah. Actually, it's kind of like that. This one is kind of weird to impress upon you why just saying these words I'm saying is so profound. So let's look at this experiment which we already looked at, which was this electrons going through the slit. So you can think about it this way. The electrons have many properties, but in this experiment, one property they can have is they went through one slit or the other. You can say that. They can't go through the barrier. Now we know that to understand this interference pattern, you have to think of the electron as being like a wave, which means in some sense it goes through both. But you can say, well, now come on, these are particles. Which one does it go through? And you could have imagined, well, speaking kind of crudely, you can imagine shrinking yourself down, getting a little flashlight, standing in one of these slits here, or maybe putting a person in each one, shining a light there and saying, electron went through. And then, the electron didn't go through. You can just say, well, and we'll figure it out. Which one did it go, which hole did the electron actually go through? It can't go through both, it's a particle. As soon as you do that measurement where you make the electron commit to which of these two possibilities it's in, these two possibilities we say are in a superposition, when you make it commit to one element of the superposition or the other, then what happens is this interference pattern goes away. And you get what you might expect, which is just two blobs where the electrons going through hit the screen back here. As soon as you stop looking at where the electrons went, this comes back. And these experiments, I'm dumbing it down a little bit, but these experiments really have been done. It's remarkable. So the electron really does, in a sense, have to go to make this pattern in this scenario. It's in a superposition of states, a superposition of locations. One here, one here. One electron, though. And it's only if you look can you see which one it goes through, but then you lose this physical effect of when it goes through both. So this is this idea of superposition. I might add that in the this is a picture of the 4th energy level of hydrogen with some angular momentum. Anyway, this is some electron. This is one electron in a hydrogen atom. This weird, very beautiful shape. Okay? You can think of it as a superposition. The electron is in all these places where the colors are. And simultaneously with various probabilities, like the traffic light, 1/3, 1/3, 1/3. And it will only look like an electron if you make it commit to where it is, but I think to do that you would just about destroy the atom. This is really a better picture of what the electron is doing. It's in a superposition of locations. And that's the right way to think of electrons and atoms. Okay, so the traffic light, red, yellow, and green is what quantum mechanics says, not red, yellow, or green. And then if you look, of course, it will be red, yellow, or green. That's the message here. Now, this sounds a little weird, I admit. And you might say, look, I may not know what color the traffic light is, but there's got to be some description of the traffic light which will tell me what color it's going to be, whether or not I look at it. And remarkably, a very, very, very brilliant physicist named Bell, John Bell, I think, is it John Bell? I think it is, yeah. No. Came up with a theoretical analysis of this sort of thing, and he derived some mathematical inequalities. And these inequalities would establish whether or not, if you could take data the way he prescribed, establish whether or not there is a description of the system which will tell you which of those superposed possibilities are actually happening. And this first experiment of this kind was done in the 1980s. So Bell did his thing in the early 60s. The technology caught up with his ideas in the 80s. And they did this experiment. This is one of many experiments usually called an aspect type experiment. And in this experiment they proved that there is no description of nature which will explain what you see and tell you which slit the electron went through or which light was lit up unless you look at it. Quite remarkable. This leads to a complaint that Einstein had about quantum theory. So Einstein is famous for not caring for quantum theory. It's a bit of a misleading statement. Einstein was one of the inventors of quantum theory. But he thought it was a good theory as far as it went, but it didn't go far enough. And there really should be a better theory which will not just give you probabilities of which red light, yellow light, or green light is on, but actually tell you which one is there, even when you don't look. But this aspect experiment shows that this can't be true. But Einstein used a thought experiment, which is really quite clever, to try to show you how ridiculous this superposition idea must be. Okay, even though now we know experimentally it's true. Okay. And I want to try to describe this experiment to you. It's kind of subtle. Okay? And so I want to try to bring it down to earth a little bit. So I'm going to dumb it down, not because you're dumb, but just because it's hard to do it in 10 minutes, right? But let me try and show you, and let me try to show it in a very comfortable way. So I'll bring in my favorite scientists, SpongeBob and Patrick Star. Okay? Now what Patrick Star and SpongeBob are going to do is they're going to look at this quantum stoplight. And this is the experiment. It's sort of a crude analog of the experiment that has been done. Okay? So what they do is they look at the light every night at midnight. They go out in Center in Maine. They look at the traffic light and they go, aha, day one, red, red. Okay, cool. Well, of course they're both red. They're on opposite sides of the light. It better be the same, right? Okay, and this happens, of course, every day because they come down every time at midnight and the lights are synchronized with the time of day, and you always get red. Okay, it's boring. But you can do this a billion times. You always see the same thing. Okay, here's another one. Okay. But then one day, SpongeBob says, I'm bored with this. I'm going to measure how big this freaking stoplight is. Okay, so he does, and he says, oh, look, it's 20 inches long. Okay, that day, Patrick sees yellow. Okay, it could have been yellow. Stoplight was in a superposition of red, yellow, and green. It could be either one of those three. This is not that big a deal. Okay, but then SpongeBob says, okay, I got that. Back to the silly game they like to play every night at midnight. Red on both sides every time. Okay, this keeps going on and on and on. And then SpongeBob says, I'm going to measure the light's size again just to double check. And Patrick says, yellow again. That's cool. All right. And now you get the pattern. Every time SpongeBob measures the light, he gets red, and Patrick gets red. Every time he measures the size of the light, Patrick gets something different. And so in my crude way, what I'm trying to show you is that, well, I'm trying to show you this, actually, that reality depends on how you observe it. Let me go back one. Every time SpongeBob, on the left, the spongy guy, every time he makes a certain measurement, it has a kind of an effect on what Patrick sees. So the whim of Patrick to measure whatever he wants affects the reality over on the other side. And so this is what happens when you have superposition properties in a quantum system. Namely, the choice of what you measure will affect the reality of how the system manifests itself. Okay. Einstein called this spooky action at a distance, and he didn't like it. Okay? But now we know experimentally this is exactly how things work. And there's a very recent experiment, I don't know when, but a few years back in Europe again, where some scientists took a bunch of atoms and they cooled them into a very cold gas, almost absolute zero. So they could get them in a very special state where they could see the superposition property. And what they did was they found that when they did this, these atoms on the left here, this is the microchip, so it's a very small experiment. These atoms on the left and these atoms on the right have various properties, and depending on what you chose to measure over here would affect what properties these atoms had over here. Okay? It's weird. So this idea that the atoms have their properties whether or not you look at them is not true. It's a very strange way of thinking. It takes a little getting used to. Okay. Let's see. I'm going to skip on. Yes, we're almost done. Let me just go one more thing, okay? There's superpositions in time. That's really wild, but let me spare you that. Let me get to the end, okay? Let me finish up. One more observation that's coming from this superposition idea. It's very cosmological. Okay. All right. So first I need some terminology. So let's think about that quantum traffic light again. The quantum traffic light had three possibilities, red, yellow, green, each one 1 in 3 chance of appearing. Okay, you could make different numbers if you want, but let's say 1 in 3. So the traffic light has sort of 3 properties at once. That's the superposition, which means, right, laying things on top of each other. And so statistically, the light has some variance, some fluctuations in what it could be. Just like in this room, if you measure all the ages, you'll get some statistical variations, right? So this thing has statistical variations which are mandated by quantum mechanics. So they're called quantum fluctuations. Okay? These quantum fluctuations are real, and they can be seen in a very striking way. So let me remind you, I'm almost done. Let me remind you about the Big Bang itself. Okay? So in the very early universe, who knows what happened when it started, but immediately after the creation of the universe by whatever process, the universe is a very dense, highly dense place to be. In fact, so dense that essentially all mass is sort of not in play. Everything is more or less energy. Okay? That's the way we model this thing. But the energy itself is something you can measure. And you know, the energy here or the energy here could be different. And these energy has various possibilities, is also in a very quantum mechanical state of mind. And so the energy actually has statistical features to it, in the sense that various energies have various probabilities for occurring at different locations. So we say there are quantum fluctuations in the energy density just after the creation of the universe. Now the universe undergoes what's called inflationary expansion. So the model that we use to explain what we see observationally is the universe expands very rapidly, very briefly, but very rapidly, for just a moment. During that time, those minute quantum fluctuations in the energy density, which are just so tiny, right? They're smaller than atoms. That's the scale where all this quantum stuff happens. They get blown up by this expansion. They get blown up to macroscopic sizes, eventually. And when things get big, like in everyday life, the quantum weirdness gets suppressed by the bigness of everything. You don't see it. We don't see any of these quantum red lights here, right? So these features, which were purely quantum mechanical, purely statistical, and a superposition feature, get embedded into the energy density of the matter that eventually makes up the universe as it expands more and more. So some places you have more energy, some places you have less. Where there's more energy, gravity clumps together and things start to form like galaxies and stars. Stars and galaxies, perhaps, in that order. Other places where there was a little less energy because of the quantum fluctuations, become more vacant and we have empty spots in the universe. So the origin of structure in the universe that we could be explained, perhaps, by this inflation of this blowing up of these minute quantum fluctuations that happened right at the very beginning of the universe. Now this sounds like a pie in the sky science fiction talk, but people have mapped out the afterglow here of the Big Bang. It's called the cosmic microwave background radiation. This is the afterglow of this big explosion, or whatever you want to call it, that starts the universe off. And the cosmic microwave background that you see has lots of clumps in it. Hotter spots, cooler spots. Now, this is happening some, I don't know, 10 to the 5th years after the origin of the universe. But you can then model the universe before this and try to see what would happen to those quantum fluctuations if they inflate and grow at this time when this afterglow was established. And you can compare the predictions of the quantum physics blown up to what you actually see. This is data taken by, I forgot which satellite, but it's from spacecraft data. A very, very detailed map of the sky looking at the afterglow of the Big Bang. And what you find, of course, or I wouldn't be telling you this, what you find is that those minute quantum fluctuations, when blown up, give exactly the pattern of light and dark that you see here. So the punchline is that while we were here to talk about the very, very small and the quantum weirdness that happens there, the universe itself has taken that stuff and blown it up so that we can actually see it in the sky. And I'm back now to our first talk of the semester or the year, which was about cosmology. So it's a good place to stop, right? I've completely closed the circle. So I'm done. Thank you for your attention. Questions? Go ahead, green shirt, I see you. Right. Shout.
So how there are different atoms and stuff, are there different types of electrons?
Are there different types of electrons? Good question. There are many electrons in the universe, right? Many. All electrons look alike. So they're all the same. They're in different places doing different things, but they're all the same. There are other particles that are electron-like, but there's only one kind of electron, if I understand your question. Other questions? Yes?
So the rules on the quantum level are different than the rules of every day. Do we understand when those rules change?
That's a great question. So she's saying, look, we got one set of rules for the little distances. We've got our everyday rules throwing balls around for the large distances. What happens? How does the interface between these two sets of rules work? Really good question. And people, it's still a research area question. So we do, theoretically, and to some extent experimentally, know how this happens. It doesn't just turn off. Quantum physics doesn't just turn off and become everyday life. But what it turns out is everyday life is the approximation to quantum physics you get when things are very large and the quantum fluctuations are very small. So this is what happens when things are large. And it sort of gradually happens to a better and better approximation as you make that transition from small to large. I don't know if that helps or not, but it kind of does. Other questions? Yes?
We were talking about quantum tunneling and the electron acting as a wave as it goes through the barrier.
Yes.
Does it go through the barrier or does it just appear on the other side?
Yes. Okay, so the question is always the same in quantum mechanics. The question is, when the electron goes through a barrier by tunneling, does it go through the barrier or just magically appear on the other side? And my answer was yes, because it's kind of interesting. If you try to actually make the electron commit to being where it is, okay, then if you look inside the barrier, you have to give it so much energy to see it, as it turns out. I'm not saying this is obvious, I'm just telling you, that you actually, it's as if you kicked it over the barrier. If you actually try to make it commit to being in the barrier. So, is it in the barrier? Is it not? You will never see it there. You will never see it there. Yeah. So that's a really good question. Yes?
Some of the experience when you say look at something, does that involve bouncing light off it?
Well, I was saying look, trying to just speak in a friendly way. But so look usually means some method of observing or determining what a property is. And so yes, look could mean bouncing light off something, but we certainly can't look at electrons that way. Because light, if you bounce light off an electron, the electron goes flying away. Whatever you're trying to measure about it has been disturbed. So look, for me, was sort of a colloquial way of saying some clever way of measuring properties. Looking at things is not the only way by any means of measuring properties, right? So does that help? Yeah. Yes, you.
How does electron
Oh, I didn't even talk about, there's lots of answers to your question. His question is, how does electromagnetism work kind of with quantum physics? That's a big subject. That's a big question. That's a great question. Okay? There's lots and lots of things, but I'll just say one thing. A favorite place for people in quantum physics to play is to manipulate another kind of particle-like, wave-like thing called the photon, which is a little packet of energy associated with electromagnetism. And so the interface between electromagnetism and quantum mechanics is really important, really deep, if that answers your question. Yeah. Other questions?
How about gravity and gravitational waves and Higgs bosons? Are they related to quantum physics?
Yes and no. So the question is gravitational waves, Higgs bosons, quantum physics. Go, right? That's sort of what you said, yeah? So yes. So let's talk about the Higgs boson. Higgs boson, definitely a quantum mechanical beast. And the Higgs boson is a particle which also has its wave-like features, but the particle part of it has been seen at that LHC I mentioned early on. That was the great discovery made there, the greatest discovery they've made. One of the biggest discoveries in the history of quantum physics was to see that Higgs boson, through experiments at the LHC. So yes, and that's a very quantum mechanical beast there. Gravitons, well, gravity and gravitational waves, if you think of them as analogous to light waves, then you'd like to find an analog of the photon for gravity waves, and those are called gravitons. Nobody's ever seen those. I would be surprised if we don't somehow see them someday in some form or another, but they are purely theoretical, for sure. Yeah. Yes?
My question was about the image that you showed us about the changing from the idea of the atom as this universal thing to the different variations and possibilities of what it looks like.
Yes.
My question, I guess I'm interested to know a little bit more about how that image is coming up. Can you explain? It's hard to communicate the question.
It's hard to answer too, because it's not something to say in 2 minutes. But so how do those pictures come about? What you're seeing in those clouds is the probability of where the electron is. Okay?
So the space is in between?
Is where the electron will. Now, if space is in between, it will be extremely unlikely to ever find an electron there.
Oh, the probability of where it is.
Yeah, and so you just say, well, okay, so what? Where is it really? You know, you don't give me probabilities. But these aspect type experiments show that probability thing is the best you can do in an atom. Yeah.
Not the movement of the electron?
Oh, you can ask for the movement of the electron. The electron certainly moves. But actually, in those atomic states, the electron doesn't have a definite position or velocity. It's in one of these superpositions where it has many velocities and many positions at once. So I only showed you the position superposition. You could also draw a map for the velocities as well. And it will be not so different looking. I don't know if this helps, but
yeah.
Okay. Other questions? Okay, well, last question, and then you should go outside and play. Yes, sir? Oh, wait. Go. Just shout it out, man. I don't hear it. Say again? Oh, that's a great question. Very good. How many molecules would it take to make something enormous? The real answer I will tell you is I don't know. But I'll give you if I was teaching a class where I had to say, here's what I would say. So this is an approximate answer. This is a guess, okay? But I would say the number of molecules you need to make something like this, or your hand, or you got a crayon or a pencil or something, it's about a 1 with 23 zeros behind it. 10 to the 23, so it's a lot. Just in something this big. Maybe it's a little less, maybe it's a little more. But a good number is 10 to the 23. A 1 with 23 zeros after it. What about the what? The sun. More. A lot more. That's a good question. Very good question. Okay, it's enough already. If you want to talk more, we can talk. Thank you.